Get started here. So thank you everybody again for joining. Welcome to today's webinar, Virtual Testing of Vishay Thermistors and RTDs with Simulink and Simscape. My name is Mike Kraus and I'll be the moderator for today's webinar. I am joined by my colleagues Alon Stas and Josh Palema. Josh and Alon have both product marketing group for the nonlinear resistors product portfolio at Vishay. They've both been with Vishay for many years now and support technical and commercial customer opportunities across the product portfolio. Following our first two webinars about electronic simulation with Vishay nonlinear resistors, we present a new simulation composed of components with software, MATLAB Simulink Simscape by MathWorks. Simscape is a multi-domain software that allows many problems to be solved in the fields of mechatronics, hydraulics, and power electronics, among others. It is thus ideal for simulating sensors and protection elements, which often bind these different domains. After a short introduction by Mr. Steve Miller, manager of the Simscape facility at MathWorks, we'll present elaborate models of Vishay nonlinear resistors already integrated in Simscape simulations. We will then show several complete applications involving these models. Emphasis will be placed on the ways thermal simulation of NTC assemblies can be managed in Simscape. Before we jump into the presentation, I just want to let you know that there will be a Q&A session following the presentation. Please use the Q&A module to ask your questions, and we will do our best to answer everything we can. A recording of this webinar will be sent afterwards, so please feel free to share it with your colleagues. With that being said, let's jump into the presentation. Josh, over to you.
Welcome to the third installment of our webinar series. In our previous sessions, we delved into the fascinating world of electronic simulation, focusing on Vishay nonlinear resistors, NTC and PTC thermistors, and RTDs. Throughout these sessions, several products were simulated in emerging application use cases through use of different EDA software, including, but not limited to, LT-Spice and QSpice. Today, we're excited to introduce our components in a powerful tool. Our new webinar is titled Virtual Testing of Vishay Nonlinear Components with MATLAB Simulink Simscape. As you will hear in a few moments from the introduction words of Steve Miller from the MathWorks, Simscape is a multi-domain simulation environment for mechatronics, hydraulics, power electronics, and provides a unified platform to tackle complex problems. Then buckle up as my Vishay colleague Alon Stas reviews meticulously crafted models of Vishay's nonlinear resistors, seamlessly integrated into complete applications, some of which are already available on MATLAB Central, making it much easier for you to dive right in. Get ready for insights that can enhance your design.
Well, thanks a lot, Josh. Hello, my name is Anastas, and before going into the core of the simulations, let's listen to a kind forward message recorded by Steve Miller, who is going to present himself and Simscape. Here it is.
Hello, my name is Steve Miller, and I'm a product manager for physical system simulation at MathWorks. I've supported Alain as he has created simulation models of thermistors and RTDs. Simscape was the perfect solution for the problems he was trying to solve because it enables virtual testing of physical systems. This speeds component selection and aids system design. Simscape lets you represent physical systems involving mechanical, thermal, electrical, and other domains as a schematic. This is perfect for the applications we're going to be looking at in this webinar, as Vishay components often serve as sensors at the boundary between multiple physical systems. Over the next 15 minutes or so, you'll see how to use simulation to create better designs for temperature sensing and circuit protection. If you like what you see, we'd be happy to help you explore virtual testing of your designs. I hope you enjoy this webinar.
After opening MATLAB, we go into the Simulink environment, where we can open the project Vishay Simscape library for NTC thermistors and RTDs. All the libraries and the simulation are installed, and then this central menu appears. The first simulation that we are going to perform is the application of a temperature step onto a thermistor. In this simulation, we compare the thermal behavior of a Vishay model with a standard thermistor model from Simscape. The Vishay model proposes supplementary features like the visualization of the response time and the self-heating. The external temperature is modeled here and is applied to the thermal pin of the thermistor. We see here a bit of self-heating at 25 degrees C as we apply a 2.5 volt onto a 1000 ohm thermistor. Then we see also the thermal response of the Vishay part. These features are not modeled for the Simscape native thermistor. We can then model the influence of the tolerances on the electrical parameters on R25 and B value. We see here the different voltage levels corresponding to nominal and also to extreme tolerances on R25 and B value for the thermistor. We can now use this dynamic NTC thermistor model and build a complete application of oven temperature sensing and control, in this case a simple on-off temperature switching. The NTC is placed in a Wheatstone bridge and its signal is compared to a given reference signal for a temperature profile reference. The Wheatstone bridge voltage is used by a comparator in order to activate a relay allowing a current to pass through a heating element. This way, the temperature of the heated object will follow the predefined temperature profile with ramps and dwells. As always, it's interesting to test an application with the introduction of tolerances on one or more elements of the circuit. In this case, it will be a tolerance on R25 and on the response time of the thermistor. We can thus verify that an excessive response time induces a high temperature overshoot. We can now study another type of application for Vishay NTC thermistors. In this case, the temperature compensation of another sensor, for example, a strain gauge probe. A resistive strain gauge sensor has a positive temperature coefficient, which can limit the temperature range for its use. Placing a network of fixed resistors with a thermistor can help to reduce the global variation of resistance in function of the temperature. While we are sweeping the temperature toward the total temperature range for a fixed strain, we see clearly the reduction of resistance variation in temperature from -13% to less than 2%. Evaluation of the effect of the NTC tolerance is of course possible, and we see here that the introduction of these tolerances does not degrade too much the results of temperature compensation. Example number 4 is about a platinum thin film RTD model, a PTS. The same dynamic characteristics, including the different tolerances that we saw for the NTC, can be reproduced for this other type of temperature sensor. Here you see the positive voltage variation on the PTS induced by the temperature step from 0 degrees C up to 150 degrees C. We can sweep the different parameters, the electrical tolerances at 0 degrees C and the tolerance on the slope, and visualize the effects on the voltage produced by the component. The fifth and last example of application based on an NTC thermistor or an RTD is a full circuit of a temperature control for a heat producing source by a Peltier thermoelectric element. While this source produces a burst of heat pulses, and also while the ambient temperature changes, the Peltier must hold this source temperature as close as possible to a given temperature profile. In order to do this, a controller uses the temperature signal given by the thermistor, measuring the temperature of the cold zone of the Peltier. The PID controller tunes then the Peltier current accordingly in order to optimize the temperature profile. Looking at the results of the simulation, we see that the temperature of the core zone follows closely the given temperature profile. On the lower pane, we see the Peltier control current variations, and we see also that at certain moments the Peltier works in reverse as a heater. On the upper pane also the temperature variation at the hot zone of the Peltier. The Vishay Simscape library project always proposes active links in order to explore the thermistor datasheets of the different components used to build the simulations. You will find a section with more information about this example as a link into the simulation. We are moving now to PTCEL application. Basically here, a tri-phase network will be rectified and will precharge a smooth capacitor. And doing this, an inrush current is generated. The function of the PTCEL is to limit this surge current while not going to protection mode in normal condition. We need to design a network of PTCEL adapted to the application conditions. That is the main voltage, the capacitor value, and the ambient temperature. For a simulation, we will need a certain number of parameters which are stored in a .mat file in MATLAB. Now that the parameters are loaded, we can go to Simulink and then open the simulation on PTCEL67. And we can examine the complete circuit comprising the tri-phase circuit, the rectifying diode bridge, the PTCEL67 network made of 4 parallel branches of 2 components placed in series, and the smoothing capacitor. The ambient temperature applied to the PTCEL is represented here with this temperature source. Let's populate an ambient temperature of 25 degrees C. Then we have here a voltage indicator which will visualize the voltage threshold for the capacitor to reach. We have also 2 scope screens, one for the current and one for the voltage on the capacitor. We have also a scope for the temperature display. Let's look briefly at the PTCEL model. The RT curve and the VDR effect are defined with 2D and 3D arrays, of course, because that's the essence of MATLAB. The thermal model of the PTCEL consists of a thermal Foster model. Each PTCEL model is defined with a facultative output thermal pin, which allows to eventually connect the PTCEL together in a thermal network, if they are thermally connected onto the board. Let's not activate these thermal pins for the moment. We are going to see a live rendition of the current decay and the voltage rise for the smooth capacitor. Parallel to that, we can evaluate the temperature rise on any of the PTCEL components. Due to the scattering of the tolerance on R25 from -30% up to +30%, the reach temperatures go from 110 degrees C up to 160 degrees C. In between, the voltage scope shows that the threshold voltage of 900 volts has been reached within the 4 seconds. If maximum 4 seconds is an acceptable timing, then we have achieved our goal. Meanwhile, the 8 PTCs have reached their maximal transient temperature and are ready for slow cooling. Let's now test a case where the ambient temperature is rising up to 50 degrees C. We will start the simulation in the new conditions of ambient temperature. And while the capacitor charges, we remark that 4 of the PTCEL see their temperature increase above 160 degrees C, which means that they are switching. It becomes clear after a few seconds that the capacitor voltage won't reach the 900 volt threshold. 4 out of the 8 PTCEL 67 are switching or already have switched and are blocking the charge. When two PTCs are placed in series, the efficiency is decreased because one is always switching before the other as they are not exactly matched. But there is a way to improve that situation by connecting thermally the two elements in series. This is what we are going to test now by activating the facultative output thermal pin. This supposes in the practice that we connect the PTCs together with thermoconductive paste, for example. The level of improvement will be depending on the value of the thermal resistance between PTCs. The first simulation that we perform with this new configuration will use a very high thermal resistance so that we can reproduce the original application. It is unlikely that we will succeed to reach 900 volts with this value, but it is a way to verify step by step that the models are working well. And okay, we see that we need now to decrease this thermal resistance between serial PTC. We can do this in the MATLAB environment, and then we can verify if the situation is now improved. Let's restart again the simulation and let's visualize the current decay and the voltage rise across the capacitor. A bit of suspense now while we are waiting. Right, this seems to be the case. The capacitor level reaches 900 volts now before 4 seconds. And still with an ambient temperature of 50 degrees C. And last but not least, we see on the temperature scope that the PTCEL temperature are now coupled 2 by 2. The last example that's going to be shown today is the fitting in Simulink Simscape of the thermal response of one of the most used Vishay sensor assemblies, an NTCALUG 01T, a surface temperature sensor. We load in MATLAB the file containing the information for the Foster model thermal time constant and the gradients for this component, and we open the simulation where an NTCALUG 01T is pressed against a hot metal plate and thus submitted to a temperature step. Here is the Foster model with 5 time constants, and here is the representation of the gradient between the surface and the lug. We add some signal names in order to visualize them on the scopes. We will represent different temperature, the initial temperature, the real physical measurement, the temperature step of the plate, the Simscape signal, and the difference between the simulation results and the physical measurement. Let's proceed to the simulation of the temperature step. Here is the Simscape's result in yellow, and if we do not see the red curve representing the real physical measurement, it's for the good reason that the matching between the simulation and the measurement is really good. This matching is better seen on another scope, which shows that the offset stays between minus 0.2 and plus 0.4 degrees C. Finally, this voltage scope will provide a voltage drop onto the sensor, which can be used to develop further the application.
Thank you both, Alon and Josh. That was a great presentation. We will now open it up for Q&A. Again, please feel free to send through any questions you have through the Q&A module. Alon and Josh, I see a few questions here. I'll start here with the first one. What are the prerequisites for beginning with Simscape and really dealing with the new models from Vishay?
Sorry, what was the question?
What are the prerequisites for beginning with Simscape and really deal with the new models from Vishay?
Yeah. In fact, you can, if you want to learn the basics of Simscape, you can do a self-paced interactive online training on the MathWorks website. There is no need to download the software. You go to MATLAB Academy and you search for the Simscape on-ramp course and then follow the steps. Of course, if you want to build your own model in Simscape, it will help that you have some knowledge of VHDL, AMS, or Verilog AMS. The most difficult point of nonlinear models like the one of Vishay is that you need to find very complicated equations to describe the models. But with MATLAB and its powerful use of arrays, it's very easy. All you need to enter is to define the properties of your component with arrays, which is the specialty of MATLAB. And once you have done this, then half the job is done.
Great, thanks for that. I have another question here. Are the models and simulations available for Vishay nonlinear in Simulink Simscape?
Yeah, the NTC and the RTD models are already introduced in MATLAB Central. For the PTC, it's another thing. We didn't do that. If somebody is interested in using PTCEL for pre-charge circuit in automotive batteries, they can contact Vishay through the address edesign.nlr@vishay.com, or they can contact Steve Miller at the MathWorks, who is responsible for the Simscape brand. So both addresses are possible. We are keen to define the models which are needed by our customers.
Great. And I have one more here for you, Alon. Some engineers are very familiar with the SPICE EDA, but not with Simscape. What does Simscape do that SPICE software cannot do?
Yeah. So you know that the thermistors are involving, of course, a very important value as the temperature. And despite all the efforts in SPICE to define the temperature, it has to be defined with a voltage. So that could be somewhat confusing for the users. Once you have done it, no problem anymore. But it's not easy to introduce the temperature, the real temperature of the device in a dynamic way in SPICE. At the contrary, Simscape is a multi-domain software. So there in Simscape, the temperature is treated as a quantity, is its own right. It's in a way, this approach by Simscape of the temperature of the component is more by the book. Also for MATLAB, the support which is given to the user will be certainly appreciated. And not last but not least, in Simscape, in contrary with SPICE, the user will be enabled to couple other domains such as liquid and gas cooling systems and multi-body physics together with the electronics. And that makes this is a very good asset of this kind of software, of being able to treat multi-body physics and not only electronics. So that's what differentiates Simscape from the SPICE program.
Great.
And that's
Thank
it.
you. Yeah, I believe that is it for questions. If you have any more questions to the audience here, please feel free to reach out to myself or Alon or Josh directly, and we will be happy to answer those for you. Like I mentioned at the beginning of the broadcast, we will be sharing the recording of this webinar.
Yeah.
So be on the lookout for that. And yes, thank you so much for Alon and Josh for your participation today. And thank you to the audience for
yeah, Mike, I have one final sentences. I have some final sentences, because finally I would like to take this opportunity to thank Mr. Steve Miller and the Simscape team from the MathWorks for not only letting me use a sponsor's version of the software, but also for having taken an active part in the uploading of the models in MATLAB Central. Many thanks to them, and also thanks to the listener. We at Vishay are looking forward to provide models of a nonlinear components, Thermistors and RTD in Simulink Simscape.
Great. Well, thank you again, and everyone, we will be sharing this presentation shortly. So have a great day.